So I'll start with an introduction here. So hello everyone, I'm Matheus Izvekov. I'm a compiler engineer and working on Clang. I work all areas of Clang front end. I'm only doing front end work. I work a lot of mostly on templates, Clang EST things. Separate project that I'm working on is template specialization resugaring, which is about solving the problem of losing type defs when you instantiate templates. Something I'm working on to upstream on Clang. It's also helpful for static analysis and things like that. Maybe the subject of future talk. This talk here is about function template partial ordering. And I'm going to start from the very basics here, get everyone up to speed. It's gonna get more advanced towards as we advance in the talk. I'll end the talk talking a little bit about core issue that I solved in Clang in this area. So, all right, let's get started. When you're in a situation where you have a function call and there are like multiple functions with the same name, multiple functions may be potentially called. Though some of those functions they are potentially called, others are not. Like for example, if you have calling a function with an int variable, functions that take pointer are not like even considered as candidates here. But all these functions that do, they form what I'm gonna call overload set here. And the process of finding the best function, which is going to be the function that is going to be called, is a process of overload resolution. And partial ordering is the last step in overload resolution before you give up and say, "Oh, this is ambiguous. We can't decide which function to call." So it has to be a single best function, right? Like two functions, as good as they are, if they match, actually match the call equally well, we're not gonna randomly pick one of them, right? We're gonna say this is ambiguous. Compiler doesn't know what to do. Your program is gonna be ill-formed, right? Um, so there are many rules to overload resolution, and the overload resolution is a very complicated subject that would take a talk on its own. The point here is not to go too much detail into that, but you gotta get situated, to understand where partial ordering applies. You have to keep overload resolution in mind when dealing with functions. So a quick overview of overload resolution. So if you have one of the candidates has a function parameter type that is an exact match, or is the exact same as the argument type, this is a perfect match, and usually you don't need to keep looking anymore. You found your best function. If that is a single function like that is your best function. Overload resolution ends there. But if you have, for example, different kinds of conversions involved for each candidate, they're gonna be like considered better because some conversions are better than considered better than others. And non-templates are always better candidates than templates, right? And certain kinds of reference are better matches for other kinds of references. But up to this point in overload resolution, we're only looking how well each function, each candidate matches the arguments for the function call that they're trying to call. When one of these candidates is a function template, then the compiler is going to generate a function template specialization from that function template by doing template argument deduction. If there is a failure in this process, then the function template simply does not participate in overload resolution. It's not considered a viable candidate, right? Um, And function template specializations, they participate in overload resolution just like any non-template function. There's no special treatment here. But this creates further challenges to overload resolution. The problem is when you have non-template functions, if they have the same signature, right, they take the same parameter types, these are not different functions, they're simply redeclarations of the same function. So there's only one candidate. But if you have multiple function templates that generate multiple function template specializations, they happen to be exactly the same, they still go in the process as separate candidates, right? So to give an example here, you have this function template that takes parameter type t, another one that takes parameter pointer type, right? And you try to call that with a pointer to int type. This is going to generate two function template specializations. So for one, it's going to generate specialization take int star, and for two is going to generate exactly the same thing. So what if you get to that point and you have a bunch of function template specializations and they match the arguments equally well, as for example that last example we just saw. That's where partial ordering kicks in, and this tiebreaker, the last step in partial ordering, before you give up and diagnose this call as ambiguous. And partial function template partial ordering, as the name implies, only applies to function templates, right? Or function templates specializations up to this point. Unlike the rest of overload resolution, partial ordering is not looking at the call anymore, like how you call the function. It's only looking at the function templates which generated the function template specializations that you started in. And the objective here is to find which function template is more specialized. So let's go back to that example, like only looking at the function templates here. So from intuition, I think this is going to be an easy one. Which function template is more specialized here?
Sorry, I can't read the blue text. what is it?
Well, sorry about that.
One gets T,
Yes.
and the other gets a pointer to you.
Yes.
Okay, thank you.
So number 2 is more specialized?
Yes. 2 is more specialized. So let's break that down. So 1 accepts any type. 2 accepts any pointer, right? A pointer is a type, but not all types are pointer. And intuitively, something that is more specialized, it works better in a more narrow set of circumstances, right? This looks like to apply to candidate number 2, right? So if the user wrote all of this, then like if it wrote 1 and it worked for pointers, because otherwise it didn't constrain users concepts of finite to say, 1 doesn't match pointers at all, doesn't work. If he said it works with pointers, but then he wrote another one that takes a pointer, then like the only rational thing is that he intends to say that that function works better for pointers, right? So what we're gonna try, we're gonna proxy which function is more specialized by looking at which one accepts strictly proper subset of types that the other one accepts. So the question that, so if you have functions A and B, does function A accept the stuff which function B accepts? And does the reverse not apply? If that's the case, then B is more specialized. So like, for example, for that example, if you have candidate 1 accepts what 2 accepts, if we try to answer that question, let's try calling 1 with the parameters of 2 as arguments, right? So we're basically gonna take 2 and synthesize arguments from its parameter list. So and we're gonna call 1 with that. So like looking at this example, we're gonna try to call 1 here with an argument that's of type U star. And the first step for calling a function template is that you're gonna apply template argument deduction to it. And template argument deduction is another complicated subject which would require another talk. But I need to get more into it because the problems of partial ordering are very tightly coupled to the limitations of template argument deduction. But what template argument deduction here is trying to figure out is that we have template parameter 1, which is t, and we're trying to deduce that template parameter where we have a single function parameter of type t as well, and the argument of type u star. So to figure out if this deduction works, what we need to do is try to balance this equation here, t equals u star. So we have to find a t which would satisfy that equation, right? Where t is the function parameter, u star is the function argument. So this is trivially self-evident. Like we start with at the step that we would end here. So we figure out if t is u star, then this deduction works and you can balance that equation. But this only answers half the question. Now we have to answer the opposite question. Does 2 accept the stuff which 1 accepts? Let's try looking at that. Now in this case, we have the opposite equation. We have u star equals t. Where we're trying to deduce u, we're going to try to find a type for u that would make that equal, but that's impossible, right? You cannot find this type because you cannot make something less pointer by changing what it points to. A pointedness cannot be subtracted from in the type system, right? So we have the full question answered here. 1 accepts the stuff which 2 accepts. 2 does not, the reverse does not, so 2 is indeed more specialized, and it is the function which would be called in the original example. Now let's look at class template partial specialization. The same rules are also used here. So let's look at this example and dig down into it a little bit more. So the rules in the standard says that to solve, to see which class template partial specialization is more specialized, including against the primary template, we make that check by rewriting those things into function templates and then applying partial ordering to that. And this is an important distinction because you skip all the rest of overload resolutions, jumping straight to partial ordering in this case. So we have this rewrite here for example number 2. We simply take the partial specialization signature, A specialized U star, make a function template taking that. So the corresponding rewrite is that. For the primary template, so you basically start by translating the primary template to a partial specialization that specializes no arguments. The second line is not valid C++, but if you try that on a compiler, the compiler will even know, say something, oh, are you trying to write the primary template here? Don't put that, just remove that to declare the primary template. So following that, this would be the rewrite for that, the primary template. And to answer that first question, so a partial specialization must be more specialized than the primary template. So before we even get to that last line in that initial example, we're gonna try to do this check now. So you can see that trivially reduces to that first answer. You can see there's a template specialization in the way. There's instead of T and U, there's an A specialization, but this reduces to an equation, and the same reasoning works here. They can find T equals U star, that balances, but you cannot make this work in the reverse. So this partial specialization is indeed more specialized, and the program is valid thus far. And now we don't need to check this again when we get to that last line, because if your explicit instantiation matches any one of the partial specializations, you don't need to check the primary template, don't need to put it in the overload set, because you already know it is less specialized, right? So I'm gonna get a little bit deeper into template argument deduction now. These rules, they don't magically find what would be the T that works for the deduction. And this plays a major role in how partial ordering works and it is effective. So template argument deduction works through a simple process of pattern matching. And there's gonna be a step at the end where we double check that P, the parameter type equals U, that we balance that equation after we have done this pattern matching. So one example of pattern matching here, if you have a function parameter of type, a function pointer type, return type T, one single function parameter type T, and an argument type that's also function pointer type. This one returns U and takes a V. For doing template argument deduction here, we start a recursive descent into both of those types. So we start by looking at these are both pointers. So this matches so far, and we keep looking deeper. Now we have two function types, and this still matches. And now at this point, we fork into two sets of deductions: one for the function type, return type, another for the parameter type. For the return type, we're gonna perform this deduction here, where we trivially deduce that T equals U. But when we get to the parameter type, we have this. We try to deduce that T equals V, but we have deduced T as U earlier, right? So this is an inconsistent deduction, and the template argument deduction fails here, and we don't need to keep looking. So this recursive descent into types has one crucial limitation. So we can't deduce certain type constructs when they appear on the function parameter type side. Like, for example, type lookup into a dependent type. So if you have a P type here, that's type name T, colon type, that's type lookup, looking for a member type, a member called type from dependent type that's potentially going to be something, for example, a class that has a member type. If you get to that point where you try to substitute T for something that doesn't have that type, or an int, something that cannot have a type, then this would fail at that point. But if you get to this point in template argument deduction, then you cannot deduce anything from this. This is not a failure, right? So we just forget that we saw this and continue as if this was okay. So this holds true even if instead of like having here type name T type. If we had std type identity T and then type lookup into that during template argument deduction, we don't have that information that type identity T type is the same as T. We can't assume that because we don't instantiate templates with dependent arguments, because for a class they can potentially be specialized for int or something like that. We don't know which specialization that would match, so this is completely opaque to deduction. Just the same, if you get into this same situation here, is the same result. You don't get any information to this. But as I said, at the end of the process, we're gonna double check the deduction, right? We're gonna get every template that we deduce, substitute it into the parameter type, and check that it matches the argument type. So this information is not gonna be completely disregarded from the process, as we will see here. So let's introduce a non-deduced mismatch into partial ordering, and things start getting more interesting. So if you look at this example, what does your intuition say about this one? Is 2 more specialized than 1? Does anyone have an intuition for this one? It's a little bit trickier than the first example. Anyone wants to guess? We will check this. So first step to check how this would work is that we're gonna rewrite this, perform this rewrite into a function templates. This rewrite will produce these, and we're gonna try to answer the question: does 1 accept everything that 2 accepts? Let's try to call 1 with the parameters of 2 to check that. So we start with this. They're both at the top level. They're both specializations of X. So this matches so far. Let's move on. We fork now for each of the arguments. For the first fork, we have T and V. So we deduce T equals V. The second one, we deduce U equals type name, V column type. This is not a non-deduced mismatch just yet, because the non-deduced things appearing, the type dependent type lookups appearing on the argument side here, not at the parameter side. Parameter is U, so we know U equals that. So let's substitute this deduction into P now and see if that worked. So we produce indeed P, which is the same as the argument type that we started with here. So this deduction worked. So that answered half the question. 1 accepts the stuff which 2 accepts. But again, that's only half the question. Now we have to ask the opposite question. Does 2 accept the stuff which 1 accepts? Let's go 2 with the argument, with the parameter 1 as the argument, and see how that goes. Now we have the reverse. They're both still template specializations of X. Move on as before. We have deduce V equals T. But now we get to that non-deduced case here. We have type name lookup on dependent type. We can see through that. So we forget we saw this deduction. Move on. Now we're going to double check that deduction work. So if we substitute the deduced parameters into P, we get with this line here, and this is not a match with the A that we started with. So the A was this one, right? TU, and we ended up with something that is a T and type name T type. So this does not match. This failed. Since it worked one direction, did not hold in the opposite. So this 2 is indeed more specialized. But now that you know this, I asked, did that match? If anyone had an intuition, didn't share, did that match your intuition? So looking a bit deeper into this, so you have one candidate that takes any two types, and you have the second candidate that also seems to take two types, but the second candidate, the second type, is dependent on the first. Does that for you make it more specialized?
Seems to be.
Yeah. So let's look at that example here, and now I'm gonna invoke Compiler Explorer. So if we feed that into, let me find the mouse pointer, and I cannot read the tabs here because it's very dark for some reason. I guess it's gonna be this one, yeah. So yeah, everyone except this, so no problem so far. Let's move on then. Now I told you that the rewrite to the function templates is the same thing. So I created this small test case here that's gonna test that hypothesis, right? These are the rewritten function template candidates for the last one. This is just a test setup here to get a function call that would match both of these, but it wouldn't be a perfect match for any of those. So you would get to partial ordering in that example. Let's see every implementation agrees so far. Oops. So you can see that unlike the first one, only Clang 20 accepts this. Every other implementation, including Clang 19, rejects this example. Now, anyone wants to guess what happened here? Like, was I lying to you? So to get a bit deeper on this, what happens here is that for function templates only, every implementation skips that last step I told you about, the template argument deduction, where we double check that the deduction worked. All these other implementations, they don't perform that check for function templates, but they do perform it for class template partial specialization. And this happens to be a subject of a core issue 2116, if anyone 60, sorry, if anyone wants to look into that. It's just that so far Clang is the only implementation that implemented a resolution for those for that issue. So but turns out that like just going to the compiler and make it perform that check wouldn't be so simple, because it would break a test case. Sorry, I didn't go back to the slides. It would break a test case like this. So this is valid. I don't need to show on the Compiler Explorer. Everyone would accept this. But this is a very reduced test case from how C++17 specifies that the equality operator of a string view works. So it's a very that was before the spaceship operator that made everything simpler. Very common implementation strategy in those cases was that you have like one function template that takes deduces two string views, and then other candidates that for each side deduces one string view, but the other ones uses SD type identity to create a non-deduced context, where the idea here is to match anything that would convert to a string view, right? SD string or pointer to a car or something like that. The way that Clang solves that problem is that when you have one function parameter and you try to perform template argument deduction on it for partial ordering, and you cannot deduce anything from that function parameter, we skip still skip the consistency check only for that parameter, right? And that allows those cases to keep working, but it still makes it so that this special case will never apply for a class template specialization rewrite, because you have single parameter type that's template specialization. So it still makes that rewrite work without breaking any existing code. And a bonus last example. Can anyone guess which is more specialized here? So if you look at this, one takes any two types. It looks obvious that both 2 and 3 are more specialized than 1, but can you decide between 2 and 3 which one is more specialized? What makes more specialized that? Second parameter is dependent on the first one, or another candidate where it must be the same type as the first one. Does anyone have guess for this one?
Well, three should be more specialized than 2.
Maybe we'll look into that right now in Compiler Explorer. Again, I think
they're specialized in different ways.
if it's this one, yes. And you can see here now the situation is reversed. Every compiler except Clang 20 accepts this, except Clang 20 thinks this is ambiguous between 2 and 3. And if you think into it, I don't think you can logically clearly establish between those two that either one accepts a strict subset of the types of the other one, right? So this is the answer Clang gives you, and supposedly as other implementations will give as well. And to double check this, let's rewrite this to same thing, but class template partial specialization this time. And let's look at what everyone says about this one. Okay, now everyone agrees, right? Everyone thinks this is ambiguous between 2 and 3 as well. So if you had to take anything away from this, understanding. So one thing that's one thing that got me is that you have to understand a little bit of overload resolution, because sometimes you try to rationalize an example and you see, why partial ordering picked something, but maybe your premise is wrong, you're looking at it wrong because it never even got to partial ordering in the first place. If you have that kind of doubt, you can perform that rewrite to class templates, and that's going to skip the rest of our resolution, and you got to get a straightforward answer, and implementations will diverge a lot less in that case. So I think that's it. Thank you. So anyone has any questions?
Is it so when I write code that specializes like this, say I have to write the code for pointers and for primitive types and for other special cases, custom overloads and stuff, this all feels like I just want an if-else chain, but I can't write an if-else chain. Is there some better way to control this where I can be more explicit?
Yeah, so
I have to rely on these implicit rules.
Yeah, so this is one thing that can be bad. If we went back to that first example, the function pointer, oftentimes the user will write implementation for one that doesn't work for pointers at all, and he will try to rely on partial warning to never call that function with one. That is a bit bad, breaks encapsulation a little bit, because sometimes you don't need to implement those two candidates in the same header even, right? Sometimes the function, for example, the function pointer one uses some technique that's not available in some platforms, and you can gracefully not provide the overload and rely on it falling back to that first one. But if you have that case where you don't intend it to work, then before C++20, you had the option of using enable if, right, as finite. You declare a dummy template parameter with the enable if on the default, or the same thing on a function parameter type, and you try to force a substitution failure when that's a pointer, right? And that will, when we building the overload set, that will make it fail when we're trying to establish, is this function viable, right? It's not gonna put it there. The other option after C++20 is that you have concepts, right? With concepts, you can add a constraint that's basically saying does not apply to pointers, right? And the concepts, they add two things, right? One, what I just said, and the other is that they add even another tiebreaker after partial ordering. So if you get over partial ordering and you get two function templates that are just otherwise identical, but they're just constrained differently, there's a process with concepts where you check, does one constraint subsume another? I'm not gonna get too much detail about that, but one constraint subsuming another means that constraint is less specialized. So that also works as a tiebreaker afterwards for that. Right? Any more questions?
Can we please see the errors for the second and last compiler explorer?
Yeah. I don't know why it does that. So you want to look at this one and look at the
one right before this one, and then the last one.
No, the before this one here.
Yeah.
So let's look at clang, and then what?
Control plus should.
Control plus, but I could click here, but I don't see the error messages. What's going on? Well, it's weird. Oh, I'm not connected to the internet. Sorry about that. So that was compiler explorer error. So like compilation failed. The HTTP request failed. That's what it
You
says.
can connect.
Sorry about that.
There's an open, not open, but there's a Wi-Fi network we can use.
Yeah, what's the name of the Wi-Fi network again?
It's
If you open it in
ACP physicist.
Physicist, right? And it's Discovery, right? Yeah.
Yeah.
Let's see if that works. So let's add an extra semicolon here, see if that compiles now. Yeah, now I get the message. And call to F is ambiguous, so showing this candidate and this candidate, right?
Yeah.
You want to look at the other one now?
Yeah, if you don't mind, the last one.
The last one or this one?
The last one after this.
Yeah.
I guess we can look at them all.
This one, yeah. So this one is gonna be this ambiguous partial specializations, right? So gotta get between the V-type one, that's the second one, and V2 one, that's the third one, right? As I said. And I mean, I can check all the compilers. I can even give you the link, but they all have the same error.
Right on. Thank you.
No worries. Right?
What
Any-
other error can they give that it's an ambiguous resolution?
Yes, it's ambiguous. Yeah, you can't establish that each one of them accepts strictly fewer types than the other ones, right?
The thing about uh, compiler errors surrounding templates is that there are two options and both are quite bad. One is that you don't give the compiler reasoning for the failure,
Yeah.
in which case it's a black box. You did something wrong, fix it. I'm not going to tell you what it is.
Yeah, I think that's the case here. Like, there's nothing like what would
And,
could
and-
the
and
compiler?
the other option is to give the compiler's reasoning, which gives that you do a single error and you get 20 pages worth of error
Yeah.
message to say, I tried this in this combination and I tried this in this combination, and it's unreadable.
Yeah, but I mean, except something like AI, like looking at your whole code, there's nothing that a compiler could suggest here that would unambiguously fix the problem, right? It could suggest, oh, maybe you don't want to declare V2, the third one, just delete that one. That would break the ambiguity, but would that make your program correct? I don't know, like the compiler could assume that, right? Maybe you do.
I think the main problem here
Yeah,
is that even if you know, okay, so I know I'm ambiguous between form 2 and form 3.
yeah.
It's not clear how I can say, oh, I meant form 3.
No, but you cannot. Yeah, the compile. You cannot say that you meant that. Like you can only think about how would I write either one of these candidates,
but-
so that it's more specialized than the other.
Assuming, ideally,
Yeah,
there are two separate programmers here.
Yeah.
Even if it's the one programmer, he
Yeah.
wears two cats.
yeah,
There's one that wrote the library with all three overloads, and then there's another who uses this library. And so there are two paths to solution. One
Yeah.
is, as a library writer, how do I write the overloads so that they don't
Yeah.
conflict? And the other is, as a library user, how do I tell the compiler, I get that you can't
Yeah.
automatically determine, I meant number 3.
yeah. So I understand your question. Yeah, so like the user of a library gets this error. It doesn't have much options, right? He have to understand the code. I mean, it is possible he could try something like, let's delete or comment one of those overloads, and see how well the program works
That's
for
only
each
a
one.
library.
Does every test pass? Then like passes for both. Then let's see which one performs better in benchmarks. It is not something that can be automated on the compiler side, right?
No, but the thing is, okay, we get it. The compiler can't always tell
Yeah.
which one to use. We're not asking the compiler to solve this problem.
Yes.
We're asking the compiler to give the user tools with which to solve the problem.
Yeah. So
And again, there are two paths here. Changing the overloads, that's something the library author can do. That's something that when I write the library, I can add concepts, I can change the precise signature, but I'm assuming, and when I write the library, I try to assume that because it creates better libraries, that whoever is going to use the library, even if it's me, cannot mutate that code. So, so there are two questions here. How I get it. It's part of formal verification. It's very hard to prove that a certain set of template functions I wrote will not conflict for any type. I get it. I'm not asking the compiler to do that. And as a library author, I have tools to resolve. I can use concept to narrow down the definitions of one of the overloads so that it will not conflict. For example, my question is towards the library user. Once the library user knows which overloads they intended, but I'm not sure they always have the tools to force that.
yeah, I mean, unless you can change, for for example, the argument type that you're calling it, if that's an option, you cannot do anything about that really, right? So the only option for the user, like, report that as a bug for the author. The lesson for the author here is not to
Don't do
let that kind of thing happen, right? Partial ordering is complicated. Don't write involve stuff that can get into ambiguity.
And if you do, use concepts to exclude the other form.
If that makes sense. Some cases you don't want to do that, right? Like, for example, if you do have a case where one function is truly more specialized, but it doesn't apply, for example, a user has to include an extra header to get that specialization, and the extra header has extra requirements, extra costs that the user might not want to buy into, right? Or if it doesn't work or apply to certain platforms, you may still want to try to do that, right? But you still have to be very careful that you're gonna get unambiguous result for everything that the user can try calling your stuff with, right? So yeah, unfortunately, that's only comes with testing. All right? Any more questions?
Is there like a flag to emit the compiler's thinking? Kind of like I know that there's a flag for vectorization. It can tell you here's why I couldn't vectorize.
Yeah. So unfortunately, not for Clang. GCC does have that flag where I forget the spelling, but it's something like either explain overload resolution partial ordering, when it's gonna go through each candidate, and explain what part of deduction failed. This might not be a great idea to enable unconditionally, because if you have a lot of candidates, then each candidate is tested against the other,
No,
right?
ideally, it would be a compiler or pragma or keyword or something you attach to the use that failed. So where because otherwise I get it for the entire program, and that
No,
makes no sense.
but even if that explanation, so there's two questions here. Is that one that will explain for everything, even the ones that we picked unambiguous answer? I don't think there's such a thing. That's like almost like a debugging thing that I never heard about. The flag that I'm talking, the GCC has, is that if you get to an ambiguous situation, then it will explain everything that it tried and why, for example, it got ambiguous between two candidates, right? But it can get ambiguous between a lot of candidates, and that means that it's going to print a lot of stuff.
But even if it succeeded, I think it chose the wrong, or chose differently than what I wanted, and I want to understand why, so I can fix the library.
Okay, that kind of debugging, I don't think anyone. I'm not super. I work on Clang. I'm not sure everything GCC is doing. They have some better stuff that are planned on bringing to Clang as well one day. But as far as I know, that's limited to explaining failures and not successes, right?
You have to, because if it's a global flag, then you drown. If it explains every successful overload resolution, template resolution, then you would drown.
Yeah, if it was like a warning flag, then like pragma, the control warning can still.
You want it on the expression you're interested in.
Yeah, I don't think that exists. That would be maybe a good idea. There are there's template. Now that I remember, that's something only Clang has. That's a template debugger. I think template might be able to give you some of that information, but it might not be very digestible. So template, everyone not familiar, is a project that started with a Clang fork. Now it's upstream. It basically gives a dump everything that your program does with templates. It's very useful for debugging template metaprogramming, right, where you got things wrong. I believe it works on a mechanism in Clang where it will still give you information about partial ordering, but it's not meant for that. So the information might not be super easy to read. Right. So any more questions?
Thank you.
No? All right. Thank you very much.